There's a card from a professor of psychiatry, psychology, and neuroscience here. That's worrisome. Anyway, so syntax trees are part of this assignment, sort of, kind of, but not really. So here's the story, okay? I'm not going to be testing them. And if you look at the spec, it says that for programs that are type correct, your compiler will be silent. And for programs that have type errors, your programs will give an error message. So on this, by the way, at this point, the input programs, the test cases will all be syntactically correct. So the errors, when there are errors, will be type errors or syntax errors, semantic errors. Okay. Then for the code generation phase, they'll be type correct and syntactically correct. So all that I care about at that point will be code generation. So the idea is that you have already been tested on and penalized, if necessary, for syntax errors. So going forward, you won't have to deal with syntax errors anymore. But what that also says is that in terms of fixing the problems, you need at least to fix problems with syntax errors. I'm sorry, let me rephrase that. Going forward, you need to fix errors such that you're able to handle syntactically correct programs. Okay, you don't have to fix errors that have to deal with that deal with syntax errors. You know what I'm saying? It's too early on a Monday. You need to be able to handle syntactically correct programs correctly. I don't really care about errors, syntax errors anymore. So, as the behavior of this on the spec says, you're supposed to detect and flag type errors. So what role do syntax trees play in that? None. Right? So I'm not going to test on them. And I'll tell you that right up front. So why do you want to build syntax trees? Because you'll get really tired of doing late nights on the next assignment. So you may as well put some investment into it now. Move the work forward, because it'll simplify your life down the road. Okay, that's it. And at this point, I hope you have some trust in me that if I say an assignment is a lot of work, that calibrates it somewhere. Okay? So many of you have been in 352 with me. You've done at least one good-sized assignment on the assignment 2. So you have some sense of, how much I exaggerate in terms of difficulty level of assignments. The last assignment, the code generation assignment, is really a lot of work. It is by far the most work of this entire project. The next one, assignment 4. Okay? It's also potentially the most difficult to debug, which is why which is one of the reasons it's an important reason why it's so much work, but it's not the only reason. The program is challenging, but it's also difficult to debug, which of course slows everything down because time dilates. Right? Each bug takes longer to fix. Here's the reason why. You take a program, you parse it, you do whatever you need to do, you generate code. You run that code through the SPIM simulator. It prints out the wrong answer. Now what? Where is the problem? So now what is, you work through the assembly code you generated to figure out where the incorrect assembly code got generated. Then you map that back into your compiler to say, why did my compiler generate this incorrect assembly code? Then you fix that problem. So there's now, it's an additional level of indirection. That's why it's so slow. So you start with a simple little factorial program in C++, compile it, it does not produce the right answer. Maybe the resulting code crashes. Maybe it produces factorial of, I don't know, produces an incorrect value. So clearly, something went wrong somewhere along the way. Right? If you're lucky, you can spot it right away and say, oh, look, it's this part of the compiler. Those things will go quickly. The low-hanging fruit will go quickly. Then things get more interesting. Okay, then things get more interesting and bugs stretch out. Like I said, because there's this level of indirection involved. You have to debug the assembly code that your compiler is generating, find out where the assembly code is wrong. And that can be time consuming, trust me. Then map it back to why is your compiler generating the wrong assembly code. And sometimes it can get really weird. So I encourage you strongly to use all of the tools at your disposal. For example, Valgrind. It's a wonderful tool. Use it. Not everyone does. You guys used it in 352, and it's really helpful for pointing out things like bad pointers. Okay, so please use it. The use debuggers. Anyway, but hang on, both of you. But so coming back to my initial comment, assignment 4 is difficult enough that also doing the syntax tree is just not worth the trouble. So there are two. It's not also doing the syntax tree as part of assignment 4 makes it yet more time consuming. So there are two options at this point. You can skip syntax trees entirely and go ahead and generate assembly code directly from the C++ parser. That, in my opinion, is more difficult. It's easier to have an intermediate step along the way because it's easier to identify bugs in your code. That's the reason I have syntax trees as part of the type checking assignment. I'm not going to check it, but it gives you some time to invest some work going forward to reduce the workload in assignment 4. Okay? Okay, Brian, you had a question.
Yeah, well, if there's a bug in the NIF stuff that it creates, how do we track that back to a line number in our C code?
In terms of, you don't have to track that back to a line number in your C code, I don't suppose.
Find out why we're generating that.
Oh, also the question is, if there's a bug in the MIPS code, how do you figure out what line number is in the C code, in your C code, in the source?
In the original program. So
the input program C. Yeah, the input program C code.
Yeah.
Oh, sure, you can generate comments in the MIPS assembly.
Oh, yeah.
Okay. John, you had a question?
Yeah, I've never actually worked with this thing called Valgrind stuff.
Uh-huh.
How do you spell it? Just
V-A-L-G-R-I-N-D.
Okay.
Valgrind. I strongly recommend getting up to speed and using it because it makes life a lot easier.
Okay. Yeah, because when I took assembly, we said just use this stuff.
No, this is not part of SPIM. It's 352.
Oh.
It's a Unix tool.
Oh, yeah, we can use that there.
Okay. So yeah, if you have questions, come talk to me or whatever. But it really helps a lot. And pointer errors are much easier dealt with. Okay. Other questions? All right. So let's see. Here's what I'm going to do, okay? In the interests of covering material that you need for your project, what I'm going to do is do a little bit more of type checking, then jump ahead and talk about some code generation, and then come back and cover some type checking stuff that we need to cover, but that's not part of your C++ project. So we'll get to that later in the semester. Okay. So let's right now just talk about some more type checking and then move ahead to code generation. So let's see, type checking. Yeah, I think this is where we had stopped over here, processing declarations. Last time we talked about how to process declarations. Essentially, the idea you process the declarations, you save the information in the symbol table. And the information you save is, for each variable, is the type and the scope. Okay. Now, I shouldn't say each variable, for each identifier. So for variables, that's type and scope. for function names, which also identifies, it's not just, well, we know the scope for the function name, which is the name itself has global scope. But you want to save the argument types, the order and number of the arguments, and the return type. So you can type check calls. There was a question on the mailing list over the weekend. What's the point of having, there's a requirement in C++ about having prototypes early. That before you see a function call, you have to either see the definition of the function or a prototype. And that's so that you have the type for the function symbol. You have the symbol table information for the function symbol, the types for the arguments, number and order, and the return type, so that you can type check the function call. Okay? That's also the reason that the language has an extern keyword in it. That's so that you can use, you can type check the print routines that we'll generate code for. So now let's go and talk about the actual checking that happens. You've processed declarations, now we'll go ahead and do checking. So what you're trying to do is that at compile time you're trying to enforce those aspects of the language, the semantic constraints that the language imposes. So for example, we've talked about type checking, right? Operators and operands must have compatible types. Okay, so if I have an expression x bracket I, then x has to be something to which the subscripting operation can be applied, namely an array. Okay. Flow of control checks. You don't have this in C++, but in C, for example, a statement like break or continue can only occur in certain specific contexts, right? If I have a goto, then that label has to appear somewhere, and there are constraints on where that label can appear, right? It can't. So checks like that, uniqueness checks, you have this in C++. A variable can be declared at most once in any given scope, right? So that's a uniqueness requirement. Case labels and switch statements must be unique. So these are checks that you can do at compile time, and generally you can integrate these with parsing. So they can happen as the parsing process occurs. They don't have to be done separately, but nevertheless it's important conceptually to realize that this is separate from the context-free skeleton of the program. So we're doing type checking. What is a type check? Well, conceptually what you're doing is when you declare a type for a variable, you as the programmer are saying, look, this variable x belongs to a specific data type. And a data type refers to a set of values plus a set of operations that are permitted on those values. Okay, so a type comes with a set of values and a set of operations. And now when you're type checking, you check the program to make certain that that promise the programmer made. The programmer says, look, by declaring x to be an int, I promise that I will only apply certain kinds of operations to x. So in the rest of the program, you check and make certain that that promise is being adhered to. If I declare x to be an array of a certain type, then I as the programmer, I'm making a promise that this variable takes on a certain set of values, possibly a certain set of values, right? Its domain is a certain set of values. And the operations that I can apply to it are given by the type. So then the rest of the program, the compiler checks to make certain that the programmer is keeping that promise. So the way you reason about types, well, the language provides a set of base types, shorts, chars, ints, signed, unsigned, whatever, all of those things that you get in C. In C++, it's a very, very simple set. There's char and int, right? You have a set of base types, and then, in general, what will happen is you'll have a set of type constructors that you can use to build up more complex types. Now, you need to reason about these more complex types, okay? And in your minds, you should separate out the simple situation that you encounter in C++ against the more general and more complex situation you can have in general, right? So in C++, the set of constructors is very limited. The only constructor that you have really are function types and array types, and even they are very, very limited. Okay, but in C, you have structs, you have arrays, you have unions, and you can nest and build, mix these things around to build up really, really complex expressions. So how does a compiler reason about these things? What a compiler does is, in the general case, it uses something called type expressions to reason about types. So what a type expression is it's a syntactic representation of the type of something. Okay, so I've declared various types, and the compiler correspondingly builds up these type expressions that capture what that type is. So base type, things like booleans, chars, ints, and floats, these are type expressions. A type name, like type def, is a type alias. That's a type expression. I can take a type constructor from my language, and different languages may have different type constructors. So I can take a type constructor, apply that to a type expression, and get other type expressions. So for example, if T is a type, then array of T is a type. So I've applied a type constructor to this type T, right? So int is a type, array of int is a type. That means array of int is a type, and so on. Records are structs, right? So if T1 and Tn are type expressions, F1 through Fn is a list of identifiers. Then record F1 of type T1 and so on, Fn of type Tn. This gives you the type of a struct. Analogously with unions. Okay. Pointers, functions. So if T1 through Tn are type expressions, then so is this tuple T1 through Tn, arrow T. And this is the type of a function that takes argument types T1 through Tn and returns something of type T. What do we do with these things? Yeah, well.
I was just quick question about what you said before. Does C++ allow multi-dimensional arrays?
Does it?
I don't know.
We can look it up. It doesn't. No.
I didn't think it did, but I just want to make sure that you said that.
It doesn't. All right, so here's a simple little program, okay? Char star star f, x is gotcha. I return the pointer to that string. And now I have some big old hairy thing. So the question is this legal? And for the time being, let's just set aside our knowledge that printf is a library routine, so it's not a language thing. But the question really is, over here, I'm making a reference to something of type character. So does this thing have type character? You can always reformulate this so that we are asking, is this thing of type character? So is this legal? How would a compiler reason about something like this? So let's see what happens. Well, from my program, I can see that I can look this up. And just regular symbol table lookup says that f is something that takes no arguments and has return type pointer to char. Right? So this is just symbol table lookup. So from this, the result of applying the function, so actually making the function call. So what happens when I make the function call? The return value is of type pointer to char. Okay, so where does this come from? Well, my type expression rules would presumably have a rule that says that if E is an expression of type T1 arrow T2, something that takes an argument of type T1 and returns an argument of type T2, and E1 is of type T1, right? So now I take this argument and I give it as an argument to E, right? So this guy is a function whose return type is T2, argument type is T1. Here's the argument type. So E applied to E1 has type T2, right? So this is a rule that allows me to reason about what happens when I put types together. Okay, so from this, I see, okay, this guy doesn't take any arguments. So think of this as void. So f is of this type. And if I give it the null argument tuple, then the result of applying f to the null tuple is the return type, which is this. So where's this rule come from? This rule is fairly generic in the sense that this is saying this is what the effect of function application is. This is the result of making a function call. But in general, these type rules come from the type rules of the language. Okay? So the language spec somewhere says, here's what happens when you evaluate an expression of this sort. Here's the resulting type. So in C++, the analogous thing is so in C++, the thing is over here when we look at the typing rules. Right, so there's a whole bunch of rules that say, here are the types of this. If this is an integer, then its type is int, blah, blah, blah. You know, so you have various things. Then the type of E is this, and the type of E is that. The rules for type checking. So C++ has a very, very simple set of type rules. Okay, because the set of types that you can construct is very, very limited. But even here, it's a fairly lengthy set of rules. So in a more complex language, you have correspondingly complex type rules. That's where these things, that's where these type rules come from. It's from the language. Okay. So now, what is star of the dereference of this? Well, presumably there's a rule somewhere that says if E is of type pointer to T, and I dereference E, then star E is of type T. Okay, so that's what it means to dereference a pointer. So analogously, this thing has type pointer to char. So from this, I can also conclude that, by the way, I can conflate that with array of char, because a pointer to char and an array of char are more or less synonymous. So if E is of type pointer to T, then E is of type array of T. Well, that is C-specific, right? You wouldn't get that in some other language. You certainly would not have that in something like Java, right? So different languages will have their own type inference rules, okay, type expression rules. So now I have this. So now I can say, okay, if I put parens around it, that doesn't change the type. So if E is of type T, then parens around E, that doesn't change the type. That's fine. 2 is of type int. That's a base type. So my type rule now says if E1 is an array of type T and E2 is an int, then so I can take an integer and I can use this to index into the array and pull out an individual element which is of type T, right? So that pulls out E1 subscript E2 is of type T. Okay? So that lets the compiler figure out that this expression is of type char. And that's what I have over there, right? So this is the type of QSort, the library routine. So I assert that without some sort of type expression mechanism along these lines, but appropriately extended to deal with more of the C language, checking a call to this type would be pretty difficult. So over here, this is a prototype. So I have a prototype. I have a type, I have a call to QSort. And the actual arguments could have arbitrarily complicated expressions like this. So the question is this call consistent with the type that is given in the prototype? Do the two match up? If they don't match up, the compiler should complain. If they do match up, the compiler should figure that out and be OK with it. So it's the compiler's job to reason about the actual arguments, like over here, figure out what the type is, and see if they match up. That's where you need type expressions. Okay, so in general, that's what the compiler is using to reason about what types match up where. And the type rules that I showed you over here, this is just a small set. These rules come from the language spec. Okay? Let's see, notions of type equivalence. I'm going to skip this sort of stuff. Type checking statements. I'm going to skip the other stuff on type expressions for now. And see, let's talk about whoops, that's not what I wanted, sorry. I now want to talk about runtime environments. So let's talk quickly about runtime environments. And then I want to talk about code generation. In order to talk about code generation, I need to talk about runtime environments. Why? Because what you're going to be doing when you do code generation is to take a computation encoded in the source language and map that to a computation in some other language, right? It's not quite the target language. It's not MIPS assembler. So it's something in between as of yet. Now, what the compiler is doing, though, is generating instructions, some sequence of instructions, so that at runtime, when that instruction sequence is executed, the computation in the source program gets carried out. Right? So the compiler has to have a very clear understanding of what is going to be happening at runtime, which is to say the compiler writer, you have to have a very clear understanding of what is going to be happening at runtime, what the execution environment looks like, so that it can then generate code to carry out the actions that the source program says it's supposed to carry out. Okay? So that's how we need to look at runtime environment. What happens at runtime, and what does the runtime environment do? What it needs to do is to manage the relationship between source program names and things that exist at runtime, runtime data objects. What do I mean by that? Well, if you write a program, let's take my favorite example, a factorial program. So a factorial program typically has a function named factorial or something to that effect. Okay, well, at runtime, you don't have the name factorial except maybe as a debugging convenience. At runtime, what you have are memory locations, addresses, registers, maybe condition codes, depending on the architecture. You don't have function names, except maybe sitting around on the side to make that simpler for debugging. So what the compiler has to do is to make that association between this thing that exists in the source program, a function named factorial, and some instruction in the code that it generates, in the assembly code or the machine code, such that when you say factorial, that maps to this particular instruction. When you say Fibonacci, that maps to some particular instruction in a program. When the program makes a function call, in the generated code, there has to be a corresponding jump or branch to some particular memory location. That's the mapping that has to be managed by the compiler. Things that exist in the source program, names of functions, they don't exist in the machine program. Okay, so the compiler has to figure out what target this function call refers to and set up the jump. In the program, you have variables like x and y and n. So you say things like if x is greater than 0. Well, at runtime, again, what you have are not variable names. What you have are memory locations. So if I say in my source program, if x is greater than 0, the compiler has to figure out, oh yeah, that refers to this memory location. So the source level construct x greater than 0 needs to map to something like load from some memory location, do some sort of a comparison operation, and so on. Okay? This relationship between source program names and runtime data objects. The compiler has to, the runtime environment takes care of managing allocation, deallocation, and accessing data objects. Okay, so when a function gets called, in the source program, you make a call to some function f. The runtime environment takes care of making sure that the stack frame gets allocated appropriately and that the stack frame gets deallocated appropriately. Okay. Managing different activations of a procedure, access to data objects at runtime. In general, this also includes heap objects, okay, which we don't get to see. In general, of course, several different activations of a procedure may be active, may be alive at the same time. And it's the runtime environment's job to make sure that they're managed appropriately. So when we talk about code generation, this is the part that gives people the most trouble. It's keeping track of, in their mind, so I'm now talking about 453 students that I've seen in the past, the one thing that people oftentimes have trouble with is separating what the compiler does at compile time and what the generated code does when executed. Okay, so there's a number of phases. The programmer writes a source program, C++. That gets compiled. What exists when? Okay, so certain things exist in the compiler. Code gets generated. That gets executed. Things that existed in the compiler may no longer exist in the code that gets executed. Okay, so it's really important to understand what exists when, and that's what we're talking about now. So in order to figure out what code the compiler needs to generate, I want to talk briefly about the assumptions that I'm going to be making. And these will be fairly simple, simplistic assumptions. They'll not cover everything, but they'll be a reasonable start. So I'm going to assume that I'm talking about sequential control flow. Okay, I don't have implicit parallelism. I don't have stuff happening concurrently on the side. So this means that at each step, control is at some one point in the program. Okay, not doing concurrency. Procedure execution, I'm making the assumption that each procedure, each function, starts execution at the beginning, and so at the beginning of the procedure body, and then it goes, in the appropriate order. When it's done, control returns to the instruction following the call, right? So I come along, I make a call. This starts the execution of the procedure beginning at the beginning of the body. When it's finished, control returns to the next instruction after the call. Okay, so these are familiar to you, but it excludes something. This assumption excludes parallelism, because that parallelism introduces a whole additional set of complexities. Multi-threading introduces a whole new set of complexities. This sequential execution model implies that there is no coroutining as an icon, and there's no backtracking as in Prolog, because that introduces additional complexities into the runtime. So this simplifies our life a lot. And what it implies, if you think about it, you'll see that this is a consequence of those assumptions. It implies that any two procedure activations must be either disjoint, or if they're overlapping, then one is completely contained in the other. You can't have overlapping partially like this. Okay, either they're disjoint or one is contained in the other. So this is kind of nice, because what that then implies is that I can manage procedure activations using a control stack. Okay, so when I enter a procedure, I push something on the stack. I push an activation record. And then when I'm done, I pop that activation record off the stack and I return to the caller. Turn that around for a second. It means that the stack frame model that we're so familiar with, right? You enter a function, you push a stack frame. When I'm done, I pop the stack frame and I return. That model changes. That straightforward, intuitive model no longer applies directly if I have program-level parallelism, or if I have coroutining, or if I have backtracking. Things get much more complex. So that's something to bear in mind. So you can take the standard stack-oriented model, for example, and you can say, OK, if I have multi-threading, then I'll have multiple stacks, and So things get complex, right? Something to bear in mind, that the familiar stack model that we have, the runtime stack, that rests on certain assumptions about execution. So here's the distinction between what exists at compile time and what exists at runtime that I mentioned earlier. At compile time, what happens is that you have this notion of environments which map names in the program, factorial, x, y, names to storage locations. Okay, so the compiler knows and keeps track of what locations different names in the program are mapped to. At runtime, what you have is program state, and the program state essentially corresponds to each location in memory having some value. So that's all you have, really. When a program is running, in terms of the hardware, all you have is that the different memory locations have different values, and the program, the CPU just fetches some instruction from some location in memory, interprets that, executes it accordingly. That causes registers and memory locations to get updated. So for our purposes, somehow there needs to be this entire mapping all the way through. And when you encounter programs like debuggers that need to interact with both the machine state, right? The debugger needs to interact with the machine state, but also needs to interact with the human being who likes things at the program source level, additional information has to be kept because it doesn't come for free. Okay, so the additional information which you get, for example, by saying -g, the additional information allows the runtime system to take this storage location to value mapping and go back and figure out the source level name. Okay? So what I'm saying here may look kind of obvious. It's like, yeah, of course, at compile time, what I have are program names in the program I'm compiling, and the compiler will figure out what locations they map to. But as I said before, consistently what people oftentimes get confused about is making the distinction between what exists at compile time, what exists within the compiler, and what exists at runtime. Okay? Some things don't exist at runtime. Mapping from names to locations doesn't exist at runtime. Okay. So let's take a real quick 2-minute break and come back, and we'll talk about